In this video, we're going to be studying dihydroxylation of alkenes. And there's two important, reagents that we need to know. And one is osmium tetroxide, and what this will do is add across the double bond to OH group. Important to also to know that this will add the two OHs to the same side, so this is syn. And in doing so, let's do the products, what I'm saying is that the two OHs will end up on the same side. Here we have two H's, but here we will have metal and metal. So that's the most important thing. We can also use, for that purpose, potassium permanganate, coal. And that will add syn. More interesting, I think, is what happens when we use peroxy acid. And here we use very frequently metachloropurbenzoic acid. And I'm going to draw that structure, say that benzoic acid is this, right? But if I want to make that a per acid, I need to add another oxygen, so it will be OH, another oxygen there. All right, and so it's metachloropurbenzoic acid, a common reagent. And so that will be the structure. What is important here, in contrast with the other reaction, is that for this reaction goes through an epoxide intermediate. So you have an oxygen that is being inserted in the double bond. And because we are under acidic condition, you form a protonated epoxide. And if you see that the structure of these intermediate is similar to the mercurinium and the bromonium ion that we have seen in other examples of alkene reactions. So unstable intermediate, similar geometry, positively charged, and the attack by the nucleophile happens at the more substituted carbon, which is this side. And what is our nucleophile here? Water. So what we will have is then the attack over here. Let's do my nucleophile lone pair. So I'm going to be attacking here, and this is opposite. And similar to all of the reactions that had this type of intermediate, chloronium, bromonium, or mercurinium, the outcome, the two substituents that we're adding, the outcome is anti. And so big difference here. So what we're going to be drawing then is now our products. Let me draw another arrow here and draw the product to that. So OHs end up opposite side. Well, here you will have initially an extra product that you will need to remove with water as a base. But your final product is a diol. That is a diol, but this is syn and this is anti. So that's the most important thing here to remember when we are studying this reaction. But now I have another example that is a little bit more complex, so we're going to go there. So let's remember this mechanism with a per acid. And the problem that I have is a different molecule. And let me just draw it here as quickly as possible. So let's see what happens. It's similar. We're going to be doing, again, with a per acid, but my substrate is different. Again, I'm treating that with a per acid, such as metachloropurbenzoic acid. So I see the conditions, and I'm going to be forming my intermediate. But the problem is asking me to explain the formation of the following product. So notice, well, yes, it's a diol, but it's not 1,2 like the other example. So there were the two OHs added in the two positions where we have the double bond. This time it's not. It's in a different place. So the question was, what is the mechanism to obtain that product. So we are going to start with the same thing. We're going to do the epoxide formation here. And when you do that with the metachlorobenzoic, you're going to do this too. This is my O. And since we are under acidic conditions, I'm going to put an H already there. So that is my intermediate. So in the epoxide like that can open up. And if it opens up, let's see what happens. It will open up and form the following carbocation. That carbocation is secondary, and so it's not that stable. But we do have an H here, a hydrogen. So what happens in this reaction is a carbocation rearrangement. So you will have a 1,2 hydride shift. And when you do that, you will create a more stable carbocation. Now, the charge is here. Remember that you have transferred that H over there. And finally, we will have the nucleophilic attack. So I'm going to draw an arrow here from this intermediate, so it is rearranged. And here, the nucleophile is water, right? So again, going back, and the difference in this product is that we can explain that by, if the epoxide is opening here, then we will form a carbocation that is secondary, and we can explain that product by doing a 1,2 hydride shift.